Chapter 2, Heating Earth's Surface and Atmosphere. From our everyday experiences, we know that the sun's rays feel warmer and paved roads become much hotter on clear, sunny days compared to overcast days. Pictures of snow-capped mountains remind us that temperatures decrease with altitude. And we know that the fury of winter is always replaced by the newness of spring. What you may not know is that these are manifestations of the same phenomenon that causes the blue color of the sky and the red color of a brilliant sunset. All these are a result of the interaction of solar radiation with Earth's atmosphere and its land-sea surface. Focus on concepts. Explain what causes the sun angle and length of daylight to change during the year and describe how these changes produce the seasons. Calculate the noon sun angle for any latitude on the equinoxes and the solstices. Define temperature and explain how it is different from the total kinetic energy contained in a substance. Contrast the concepts of latent heat and sensible heat. List and describe the three mechanisms of heat transfer. Sketch and label a diagram that shows the fate of incoming solar radiation. Explain what causes blue skies and red sunsets. Explain what is meant by the statement "the atmosphere is heated from the ground up." Describe the role of water vapor and carbon dioxide in producing the greenhouse effect. Sketch and label a diagram illustrating Earth's heat budget. Earth-Sun relationships. Heating Earth's surface and atmosphere. Understanding seasons. The amount of solar energy received at any location varies with latitude, time of day, and season of the year. Contrasting images of polar bears and perpetual ice and palm trees along a tropical beach serve to illustrate the extremes. Figure 2.1. The unequal heating of Earth's land-sea surface creates winds and drives the ocean's currents, which in turn transport heat from the tropics toward the poles in an unending attempt to balance energy inequalities. The consequences of these processes are the phenomena we call weather. If the sun were turned off, global winds and ocean currents would quickly cease. Yet as long as the sun shines, winds will blow and weather will persist. So to understand how the dynamic weather machine works, we must know why different latitudes receive different quantities of solar energy and why the amount of solar energy received changes during the course of a year to produce the seasons. Earth's motions. Earth has two principal motions: rotation and revolution. Rotation is the spinning of Earth on its axis that produces the daily cycle of day and night. The other motion, revolution, refers to Earth's movement in a slightly elliptical orbit around the Sun. The distance between Earth and Sun averages about 150 million kilometers, 93 million miles. Because Earth's orbit is not perfectly circular, however, the distance varies during the course of a year. Each year, on about January 3, our planet is about 147.3 million kilometers, 91.5 million miles, from the Sun, closer than at any other time, a position called perihelion. About 6 months later, on July 4, Earth is about 152.1 million kilometers, 94.5 million miles, from the Sun, farther away than at any other time, a position called aphelion. Although Earth is closest to the Sun and receives up to 7% more energy in January than in July, this difference plays only a minor role in producing seasonal temperature variations, as evidenced by the fact that Earth is closest to the Sun during the Northern Hemisphere winter. What causes the seasons? If variations in the distance between the Sun and Earth do not cause seasonal temperature changes, what does? The gradual but significant change in day length certainly accounts for some of the difference we notice between summer and winter. Furthermore, a gradual change in the angle, altitude, of the Sun above the horizon is also a major contributing factor, Figure 2.2. For example, someone living in Chicago, Illinois, experiences the noon sun highest in the sky in late June. But as summer gives way to autumn, the noon sun appears lower in the sky, and sunset occurs earlier each evening. The seasonal variation in the angle of the Sun above the horizon affects the amount of energy received at Earth's surface in two ways. First, when the Sun is directly overhead, at a 90 degrees angle, the solar rays are most concentrated and thus most intense. At lower Sun angles, the rays become more spread out and less intense, Figure 2.3. You have probably experienced this when using a flashlight. If the beam strikes a surface perpendicularly, a small intense spot is produced. By contrast, if the flashlight beam strikes at any other angle, the area illuminated is larger, but noticeably dimmer. Second, but of less significance, the angle of the Sun determines the path solar rays take as they pass through the atmosphere, Figure 2.4. When the Sun is directly overhead, the rays strike the atmosphere at a 90 degrees angle and travel the shortest possible route to the surface. This distance is referred to as 1 atmosphere. However, rays entering the atmosphere at a 30 degrees angle must travel twice this distance before reaching the surface, while rays at a 5 degrees angle travel through a distance roughly equal to the thickness of 11 atmospheres, Table 2.1. The longer the path, the greater the chance that sunlight will be dispersed by the atmosphere, which reduces the intensity at the surface. These conditions account for the fact that we cannot look directly at the midday sun, but we enjoy gazing at a sunset. It is important to remember that Earth's shape is spherical. Hence, on any given day, the only places that will receive vertical, 90 degrees, rays from the sun are located along one particular line of latitude. As we move either north or south of this location, the sun's rays strike at decreasing angles. Thus, the nearer a place is situated to the latitude receiving the vertical rays of the sun, the higher will be its noon sun, and the more concentrated will be the radiation it receives. In summary, the most important reasons for variations in the amount of solar energy reaching a particular location are the seasonal changes in the angle at which the sun's rays strike the surface and changes in the length of daylight. Earth's orientation. What causes fluctuations in sun angle and length of daylight during the course of a year? Variations occur because Earth's orientation to the sun continually changes. Earth's axis, the imaginary line through the poles around which Earth rotates, is not perpendicular to the plane of its orbit around the sun, called the plane of the ecliptic. Instead, it is tilted 23.5 degrees from the perpendicular, called the inclination of the axis. If the axis were not inclined, Earth would lack seasons. Because the axis remains pointed in the same direction, toward the North Star, the orientation of Earth's axis to the sun's rays is constantly changing, figure 2.5. For example, on one day in June each year, Earth's position in orbit is such that the northern hemisphere is leaning 23.5 degrees toward the sun, left in figure 2.5. 6 months later, in December, when Earth has moved to the opposite side of its orbit, the northern hemisphere leans 23.5 degrees away from the sun, figure 2.5, right. On days between these extremes, Earth's axis is leaning at amounts less than 23.5 degrees to the rays of the sun. This change in orientation causes the spot where the sun's rays are vertical to make an annual migration from 23.5 degrees north of the equator to 23.5 degrees south of the equator. In turn, this migration causes the angle of the noon sun to vary by up to 47 degrees, 23.5 plus 23.5, for many locations during a year. A mid-latitude city such as New York, for instance, has a maximum noon sun angle of 73.5 degrees when the sun's vertical rays have reached their farthest northward location in June and a minimum noon sun angle of 26.5 degrees 6 months later, figure 2.6. Students sometimes ask, is the sun ever directly overhead anywhere in the United States? Yes, but only in the state of Hawaii. Honolulu, located on the island of Oahu at about 21 degrees north latitude, experiences a 90 degrees sun angle twice each year, once at noon on about May 27 and again at noon on about July 20. All of the other states are located north of the Tropic of Cancer and therefore never experience the vertical rays of the sun. Solstices and equinoxes. And a half based on the annual migration of the direct rays of the sun, 4 days each year are especially significant. On June 21 or 22, the vertical rays of the sun strike 23.5 degrees north latitude, 23.5 degrees north of the equator, a line of latitude known as the Tropic of Cancer, figure 2.5. For people living in the northern hemisphere, June 21 or 22 is known as the summer solstice, the first official day of summer, see box 2.1. 6 months later, on December 21 or 22, Earth is in an opposite position, with the sun's vertical rays striking at 23.5 degrees south latitude. This line is known as the Tropic of Capricorn. For those in the northern hemisphere, December 21 or 22 is the winter solstice, the first day of winter. However, on this same day people in the southern hemisphere are experiencing their summer solstice. Box 2-1. When are the seasons? Have you ever been caught in a snowstorm around Thanksgiving, even though winter does not begin until December 21? Or perhaps you have endured several consecutive days of 100 degrees temperatures although summer has not officially started. The idea of dividing the year into 4 seasons originated from the Earth-Sun relationships discussed in this chapter, Table 2a. This astronomical definition of the seasons defines winter, Northern Hemisphere, as the period from the winter solstice, December 21-22, to the spring equinox, March 21-22, and so forth. This is also the definition used most widely by the news media, yet it is not unusual for portions of the United States and Canada to have significant snowfalls weeks before the official start of winter, Table 2a. Because the weather phenomena we normally associate with each season do not coincide well with the astronomical seasons, meteorologists prefer to divide the year into 4 3-month periods based primarily on temperature. Thus, winter is defined as December, January, and February, the 3 coldest months of the year in the Northern Hemisphere. Summer is defined as the 3 warmest months, June, July, and August. Spring and autumn are the transition periods between these 2 seasons, Figure 2a. Inasmuch as these 4 3-month periods better reflect the temperatures and weather that we associate with the respective seasons, this definition of the seasons is more useful for meteorological discussions. The equinoxes occur midway between the solstices. September 22 or 23 is the date of the autumnal, fall, equinox in the Northern Hemisphere, and March 21 or 22 is the date of the spring equinox, also called the vernal equinox. On these dates the vertical rays of the Sun strike the equator, 0 degrees latitude, because Earth's position is such that its axis is tilted neither toward nor away from the Sun. The length of daylight versus darkness is also determined by the position of Earth relative to the Sun's rays. The length of daylight on June 21, the summer solstice in the Northern Hemisphere, is greater than the length of night. This fact can be established by examining Figure 2.7, which illustrates the circle of illumination, that is, the boundary separating the dark half of Earth from the lighted half. The length of daylight is established by comparing the fraction of a line of latitude that is on the day side of the circle of illumination with the fraction on the night side. Notice that on June 21 all locations in the Northern Hemisphere experience longer periods of daylight than darkness, Figure 2.7. By contrast, during the December solstice the length of darkness exceeds the length of daylight at all locations in the Northern Hemisphere. For example, consider New York City, about 40 degrees north latitude, which has about 15 hours of daylight on June 21 and only 9 hours on December 21. Also note from Table 2.2 that the farther north a location is from the equator on June 21, the longer the period of daylight. When you reach the Arctic Circle, 66.5 degree north latitude, the length of daylight is 24 hours. Places located at or north of the Arctic Circle experience the midnight sun, which does not set for a period that ranges from 1 day to about 6 months, Figure 2.8. As a review of the characteristics of the summer solstice for the Northern Hemisphere, examine Figure 2.7 and Table 2.2 and consider the following. 1. The date of occurrence is June 21 or 22. 2. The vertical rays of the Sun are striking the Tropic of Cancer, 23.5 degree north latitude. 3. Locations in the Northern Hemisphere are experiencing their longest length of daylight and highest sun angle. The opposite is true for the Southern Hemisphere. 4. The farther north a location is from the equator, the longer the period of daylight, until the Arctic Circle is reached, where the length of daylight becomes 24 hours. The opposite is true for the southern hemisphere. The winter solstice facts are the reverse. It should now be apparent why a mid-latitude location is warmest in the summer, when the days are longest and the angle of the sun is highest. During an equinox, meaning equal night, the length of daylight is 12 hours everywhere on Earth because the circle of illumination passes directly through the poles, thus dividing the lines of latitude in half. These seasonal changes, in turn, cause the month-to-month variations in temperature observed at most locations outside the tropics. Figure 2.9 shows mean monthly temperatures for selected cities at different latitudes. Notice that the cities located at more poleward latitudes experience larger temperature differences from summer to winter than do cities located near the equator. Also notice that temperature minimums for southern hemisphere locations occur in July, whereas they occur in January for most places in the northern hemisphere. In summary, seasonal fluctuations in the amount of solar energy reaching various places on Earth's surface are caused by the migrating vertical rays of the sun and the resulting variations in sun angle and length of daylight. All locations situated at the same latitude have identical sun angles and lengths of daylight. If the Earth-Sun relationships previously described were the only controls of temperature, we would expect these places to have identical temperatures as well. Obviously, such is not the case. Although the angle of the sun above the horizon and the length of daylight are the primary controls of temperature, other factors must be considered, a topic that will be addressed in Chapter 3. Students sometimes ask, where is the land of the midnight sun? Any place located north of the Arctic Circle, 66.5° north latitude, or south of the Antarctic Circle, 66.5° south latitude, experiences 24 hours of continuous daylight, or darkness, at least one day each year. The closer a place is to a pole, the longer the period of continuous daylight, or darkness. Someone stationed at either pole will experience 6 months of continuous daylight followed by 6 months of darkness. Thus, the land of the midnight sun refers to any location where the latitude is greater than 66.5°, such as the northern portions of Alaska, Canada, Russia, and Scandinavia, as well as most of Antarctica. Energy, temperature, and heat. The universe is made up of a combination of matter and energy. The concept of matter is easy to grasp because it is the stuff we can see, smell, and touch. Energy, on the other hand, is abstract and therefore more difficult to describe and understand. Energy comes to Earth from the Sun in the form of electromagnetic radiation, which we see as light and feel as heat. There are countless places and situations where energy is present, in the food we eat, the water located at the top of a waterfall, and the waves that break along the shore. Forms of energy. Energy can be defined simply as the capacity to do work. Work is done whenever matter moves. Common examples include the chemical energy from gasoline that powers automobiles, the heat energy from stoves that excites water molecules, boils water, and the gravitational energy that has the capacity to move snow down a mountain slope in the form of an avalanche. These examples illustrate that energy takes many forms and can also change from one form to another. For example, the chemical energy in gasoline is first converted to heat in the engine of an automobile, which is then converted to mechanical energy that moves the automobile along. You are undoubtedly familiar with some of the common forms of energy, such as heat, chemical, nuclear, radiant, light, and gravitational energy. Energy is also placed into one of two major categories: kinetic energy and potential energy. Kinetic energy. Energy associated with an object by virtue of its motion is described as kinetic energy. A simple example of kinetic energy is the motion of a hammer when driving a nail. Because of its motion, the hammer is able to move another object, do work. The faster the hammer is swung, the greater its kinetic energy, energy of motion. Similarly, a larger, more massive, hammer possesses more kinetic energy than a smaller one, provided that both are swung at the same velocity. Likewise, the winds associated with a hurricane possess much more kinetic energy than do light, localized breezes because they are both larger in scale, cover a larger area, and travel at higher velocities. Kinetic energy is also significant at the atomic level. All matter is composed of atoms and molecules that are continually vibrating, and by virtue of this motion have kinetic energy. For example, when a pan of water is placed over a fire, the water becomes warmer because the fire causes the water molecules to vibrate faster. Thus, when a solid, liquid, or gas is heated, its atoms or molecules move faster and possess more kinetic energy. Potential energy. As the term implies, potential energy has the capability to do work. For example, large hailstones suspended by an updraft in a towering cloud have potential energy. Should the updraft subside, these hailstones may fall to earth and do destructive work on roofs and vehicles. Many substances, including wood, gasoline, and the food you eat, contain potential energy, which is capable of doing work given the right circumstances. Temperature. Humans think of temperature as how warm or cold an object is with respect to some standard measure. However, our senses are often poor judges of warm and cold. See students sometimes ask, p46. Temperature is a measure of the average kinetic energy of the atoms or molecules in a substance. When a substance gains energy, its particles move faster and its temperature rises. By contrast, when energy is lost, the atoms and molecules vibrate more slowly and its temperature drops. In the United States, the Fahrenheit scale is used most often for everyday expressions of temperature. However, scientists in the majority of other countries use the Celsius and Kelvin temperature scales. A discussion of these scales is provided in Chapter 3. It is important to note that temperature is not a measure of the total kinetic energy of an object. For example, a cup of boiling water has a much higher temperature than a bathtub of lukewarm water. However, the quantity of water in the cup is small, so it contains far less kinetic energy than the water in the tub. Much more ice would melt in the tub of lukewarm water than in the cup of boiling water. The temperature of the water in the cup is higher because the atoms and molecules are vibrating faster, but the total amount of kinetic energy, also called thermal energy, is much smaller because there are fewer particles. Students sometimes ask, what would the seasons be like if Earth were not tilted on its axis? The most obvious change would be that all locations on the globe would experience 12 hours of daylight every day of the year. Moreover, for any latitude, the sun would always follow the path it does during an equinox. There would be no seasonal temperature changes, and daily temperatures would be roughly equivalent to the average for that location. Heat. We define heat as energy transferred into or out of an object because of temperature differences between that object and its surroundings. If you hold a hot mug of coffee, your hand will begin to feel warm or even hot. By contrast, when you hold an ice cube, heat is transferred from your hand to the ice cube. Heat flows from a region of higher temperature to one of lower temperature. Once the temperatures become equal, heat flow stops. Meteorologists further subdivide heat into two categories, latent heat and sensible heat. Latent heat is the energy involved when water changes from one state of matter to another, when liquid water evaporates and becomes water vapor, for example. During evaporation, heat is required to break the hydrogen bonds between water molecules that occurs when water vapor escapes a water body. Because the most energetic water molecules escape, the average kinetic energy, temperature, of the water body drops. Therefore, evaporation is a cooling process, something you may have experienced upon stepping out, dripping wet, from a swimming pool or bathtub. The energy absorbed by the escaping water vapor molecules is termed latent heat, meaning hidden, because it does not result in a temperature increase. The latent heat stored in water vapor is eventually released in the atmosphere during condensation, when water vapor returns to the liquid state during cloud formation. Therefore, latent heat is responsible for transporting considerable amounts of energy from Earth's land-sea surface to the atmosphere. By contrast, sensible heat is the heat we can feel and measure with a thermometer. It is called sensible heat because it can be sensed. Warm air that originates over the Gulf of Mexico and flows into the Great Plains in the winter is an example of the transfer of sensible heat. Mechanisms of heat transfer. The flow of energy can occur in three ways: conduction, convection, and radiation, Figure 210. Although they are presented separately, all three mechanisms of heat transfer can operate simultaneously. In addition, these processes may transfer heat between the Sun and Earth and between Earth's surface, the atmosphere, and outer space. Conduction. Anyone who attempts to pick up a metal spoon left in a boiling pot of soup realizes that heat is transmitted along the entire length of the spoon. The transfer of heat in this manner is called conduction. The hot soup causes the molecules at the lower end of the spoon to vibrate more rapidly. These molecules and free electrons collide more vigorously with their neighbors and so on up the handle of the spoon. Thus, conduction is the transfer of heat through electron and molecular collisions from one molecule to another. The ability of substances to conduct heat varies considerably. Metals are good conductors, as those of us who have touched a hot spoon have quickly learned. Air, in contrast, is a very poor conductor of heat. Consequently, conduction is important only between Earth's surface and the air immediately in contact with the surface. As a means of heat transfer for the atmosphere as a whole, conduction is the least significant and can be disregarded when considering most meteorological phenomena. Objects that are poor conductors, such as air, are called insulators. Most objects that are good insulators, such as cork, plastic foam, or goose down, contain many small air spaces. The poor conductivity of the trapped air gives these materials their insulating value. Snow is also a poor conductor, good insulator, and like other insulators, it contains numerous air spaces that impair the flow of heat. This is why wild animals may burrow into a snowbank to escape the cold. The snow, like a down-filled comforter, does not supply heat, it simply retards the loss of the animal's own body heat. Convection. Much of the heat transport in Earth's atmosphere and oceans occurs by convection. Convection is heat transfer that involves the actual movement or circulation of a substance. It takes place in fluids, liquids such as water and gases such as air, where the material is able to flow. The pan of water being heated over a campfire in Figure 2.10 illustrates the nature of a simple convective circulation. The fire warms the bottom of the pan, which conducts heat to the water inside. Because water is a relatively poor conductor, only the water in close proximity to the bottom of the pan is heated by conduction. Heating causes water to expand and become less dense. Thus, the hot, buoyant water near the bottom of the pan rises, while the cooler, denser water above sinks. As long as the water is heated from the bottom and cools near the top, it will continue to turn over, producing a convective circulation. In a similar manner, some of the air in the lowest layer of the atmosphere that was heated by radiation and conduction is transported by convection to higher layers of the atmosphere. For example, on a hot, sunny day the air above a plowed field will be heated more than the air above the surrounding woodlands. As warm, less dense air above the plowed field buoys upward, it is replaced by the cooler air above the woodlands, Figure 2.11. In this way a convective flow is established. The warm parcels of rising air are called thermals and are what hang glider pilots use to keep their crafts soaring. Convection of this type not only transfers heat but also transports moisture aloft. The result is an increase in cloudiness that frequently can be observed on warm summer afternoons. On a much larger scale is the global convective circulation of the atmosphere, which is driven by the unequal heating of Earth's surface. These complex movements are responsible for the redistribution of heat between hot equatorial regions and frigid polar latitudes and will be discussed in detail in Chapter 7. Students sometimes ask, in the morning when I get out of bed, why does the tile flooring in the bathroom feel much colder than the carpeted area, even though both materials are the same temperature? The difference you feel is due mainly to the fact that floor tile is a much better conductor of heat than carpet. Hence, heat is more rapidly conducted from your bare feet to the tile floor than from your bare feet to the carpeted floor. Even at room temperature, 20 degrees Celsius 68 degrees Fahrenheit, objects that are good conductors can feel chilly to the touch. Remember, body temperature is about 37 degrees Celsius 98.6 degrees Fahrenheit. Atmospheric circulation consists of vertical as well as horizontal components, so both vertical and horizontal heat transfer occurs. Meteorologists often use the term convection to describe the part of the atmospheric circulation that involves upward and downward heat transfer. By contrast, the term advection is used to denote the primarily horizontal component of convective flow. The common term for advection is wind, a phenomenon we will examine closely in later chapters. Residents of the mid-latitudes often experience the effects of heat transfer by advection. For example, when frigid Canadian air invades the Midwest in January, it brings bitterly cold winter weather. Radiation. The third mechanism of heat transfer is radiation. Unlike conduction and convection, radiation is the only mechanism of heat transfer that can travel through the vacuum of space and thus is responsible for solar energy reaching Earth. Solar radiation. The sun is the ultimate source of energy that drives the weather machine. We know that the sun emits light and heat energy as well as the rays that darken skin pigmentation. Although these forms of energy constitute a major portion of the total energy that radiates from the sun, they are only a part of a large array of energy called radiation, or electromagnetic radiation. This array or spectrum of electromagnetic energy is shown in Figure 2.12. All types of radiation, whether X-rays, radio waves, or heat waves, travel through the vacuum of space at 300,000 kilometers, 186,000 miles, per second, a value known as the speed of light. To help visualize radiant energy, imagine ripples made in a calm pond when a pebble is tossed in. Like the waves produced in the pond, electromagnetic waves come in various sizes, or wavelengths, the distance from one crest to the next, Figure 2.12. Radio waves have the longest wavelengths, up to tens of kilometers in length. Gamma waves are the shortest, at less than 1/1000th of a centimeter long. Visible light is roughly in the middle of this range. Radiation is often identified by the effect that it produces when it interacts with an object. The retinas of our eyes, for instance, are sensitive to a range of wavelengths called visible light. We often refer to visible light as white light because it appears white in color. It is easy to show, however, that white light is really an array of colors, each color corresponding to a specific range of wavelengths. By using a prism, white light can be divided into the colors of the rainbow, from violet with the shortest wavelength, 0.4 micrometer, μm, 1 micrometer is 1/1000th of a meter, to red with the longest wavelength, 0.7 micrometer, Figure 2.13. Located adjacent to the color red, and having a longer wavelength, is infrared radiation, which cannot be seen by the human eye but is detected as heat. Only the infrared energy that is nearest the visible part of the spectrum is intense enough to be felt as heat and is referred to as near infrared. On the opposite side of the visible range, located next to violet, the energy emitted is called ultraviolet radiation and consists of wavelengths that may cause sunburned skin. Although we divide radiant energy into categories based on our ability to perceive them, all wavelengths of radiation behave similarly. When an object absorbs any form of electromagnetic energy, the waves excite subatomic particles, electrons. This results in an increase in molecular motion and a corresponding increase in temperature. Thus, electromagnetic waves from the Sun travel through space and, upon being absorbed, increase the molecular motion of other molecules, including those that make up the atmosphere, Earth's land-sea surfaces, and human bodies. One important difference among the various wavelengths of radiant energy is that shorter wavelengths are more energetic. This accounts for the fact that relatively short, high-energy, ultraviolet waves can damage human tissue more readily than can similar exposures to longer wavelength radiation. The damage can result in skin cancer and cataracts. It is important to note that the Sun emits all forms of radiation, as shown in Figure 2.12, but in varying quantities. Over 95% of all solar radiation is emitted in wavelengths between 0.1 and 2.5 micrometers, with much of this energy concentrated in the visible and near-infrared parts of the electromagnetic spectrum, Figure 2.14. The narrow band of visible light, between 0.4 and 0.7 micrometer, represents over 43% of the total energy emitted. The bulk of the remainder lies in the infrared zone, 49%, and ultraviolet, UV, section, 7%. Less than 1% of solar radiation is emitted as X-rays, gamma rays, and radio waves. Laws of radiation. To obtain a better appreciation of how the Sun's radiant energy interacts with Earth's atmosphere and land-sea surface, it is helpful to have a general understanding of the basic radiation laws. Although the mathematics of these laws is beyond the scope of this text, the concepts are fundamental to understanding radiation. 1. All objects continually emit radiant energy over a range of wavelengths. Thus, not only do hot objects such as the Sun continually emit energy, but Earth does as well, even the polar ice caps. 2. Hotter objects radiate more total energy per unit area than do colder objects. The Sun, which has a surface temperature of 6,000 K, 10,000 degrees Fahrenheit, emits about 160,000 times more energy per unit area than does Earth, which has an average surface temperature of 288 K, 59 degrees Fahrenheit. This concept is called the Stefan-Boltzmann law and is expressed mathematically in box 2.2. 3. Hotter objects radiate more energy in the form of short wavelength radiation than do cooler objects. We can visualize this law by imagining a piece of metal that, when heated sufficiently, as occurs in a blacksmith's shop, produces a white glow. As it cools, the metal emits more of its energy in longer wavelengths and glows a reddish color. Eventually, no light is given off, but if you place your hand near the metal, the still longer infrared radiation will be detectable as heat. The Sun radiates maximum energy at 0.5 micrometer, which is in the visible range, Figure 2.14. The maximum radiation emitted from Earth occurs at a wavelength of 10 micrometers, well within the infrared, heat, range. Because the maximum Earth radiation is roughly 20 times longer than the maximum solar radiation, it is often referred to as long-wave radiation, whereas solar radiation is called short-wave radiation. This concept, known as Wien's displacement law, is expressed mathematically in box 2.2. 4. Objects that are good absorbers of radiation are also good emitters. Earth's surface and the Sun are nearly perfect radiators because they absorb and radiate with nearly 100% efficiency. By contrast, the gases that compose our atmosphere are selective absorbers and emitters of radiation. For some wavelengths the atmosphere is nearly transparent, little radiation absorbed. For others, however, it is nearly opaque, absorbs most of the radiation that strikes it. Experience tells us that the atmosphere is quite transparent to visible light emitted by the Sun because it readily reaches Earth's surface. To summarize, although the Sun is the ultimate source of radiant energy, all objects continually radiate energy over a range of wavelengths. Hot objects, such as the Sun, emit mostly short-wave, high-energy radiation. By contrast, most objects at everyday temperatures, Earth's surface and atmosphere, emit long-wave, low-energy radiation. Objects that are good absorbers of radiation, such as Earth's surface, are also good emitters. By contrast, most gases are good absorbers, emitters, only in certain wavelengths but poor absorbers in other wavelengths. Box 2-2. Radiation laws. All bodies radiate energy. Both the rate and the wavelength of radiation emitted depend on the temperature of the radiating body. Stefan-Boltzmann law. This law mathematically expresses the rate of radiation emitted per unit area, E equals sigma times T to the fourth. E, the rate of radiation emitted by a body, is proportional to the fourth power of the body's temperature, T. The Stefan-Boltzmann constant, sigma, is equal to 5.67 times 10 to the minus 8 watt per squared meter times Kelvin to the fourth. Compare the difference between the radiation emission from the Sun and Earth. The Sun, with an average temperature of 6,000 Kelvin, emits 73,483,200 watts per square meter. E equals 5.67 times 10 to the minus 8 watt per squared meter per Kelvin to the fourth, times 6,000 Kelvin to the fourth, equals 73,483,200 watt per squared meter. By contrast, Earth has an average temperature of only 288 Kelvin. If we round the value to 300 Kelvin, we have E equals 5.67 times 10 to the minus 8 watt per squared meter per Kelvin to the fourth, times 300 Kelvin to the fourth, equals 459 watt per squared meter. The Sun has a temperature that is approximately 20 times higher than that of Earth, and thus it emits approximately 160,000 times more radiation per unit area. This makes sense because 20 to the fourth equals 160,000. Wien's displacement law. Wien's displacement law describes mathematically the relationship between the temperature, T, of a radiating body and its wavelength of maximum emission delta max equals C divided by T. Wien's constant, C, is equal to 2898 micrometer times Kelvin. If we use the Sun and Earth as examples, we find delta max for the Sun equals 2898 micrometer times Kelvin divided by 6000 Kelvin, equals 0.483 micrometer, and delta max for the Earth equals 2898 micrometer times Kelvin divided by 300 Kelvin, equals 9.66 micrometer. Note that the Sun radiates its maximum energy within the visible portion of the electromagnetic spectrum. The cooler Earth radiates its maximum energy in the infrared portion of the electromagnetic spectrum. The ultraviolet index. Most people welcome sunny weather. On warm days, when the sky is cloudless and bright, many spend a great deal of time outdoors soaking up the sunshine, figure 2b. For many, the goal is to develop a dark tan, one that sunbathers often describe as healthy looking. Ironically, there is strong evidence that too much sunshine, specifically, too much ultraviolet radiation, can lead to serious health problems, mainly skin cancer and cataracts of the eyes. Since June 1994, the National Weather Service, NWS, has issued the Next Day Ultraviolet Index, UVI, for the United States to warn the public of potential health risks of exposure to sunlight, figure 2c. The UV index is determined by taking into account the predicted cloud cover and reflectivity of the surface, as well as the sun angle and atmospheric depth for each forecast location. Because atmospheric ozone strongly absorbs ultraviolet radiation, the extent of the ozone layer is also considered. The UVI values lie on a scale from 0 to 15, with larger values representing greatest risk. The U.S. Environmental Protection Agency has established 5 exposure categories based on UVI values: low, moderate, high, very high, and extreme. Table 2b. Precautionary measures have been developed for each category. The public is advised to minimize outdoor activities when the UVI is very high or extreme. Sunscreen with a sun protection factor, SPF, of 15 or higher is recommended for all exposed skin. This is especially important after swimming or while sunbathing, even on cloudy days with the UVI in the low category. The public is advised to minimize outdoor activities when the UVI is very high or extreme. Table 2b shows the range of minutes to burn for the most susceptible skin type, pale or milky white, for each exposure category. Note that the exposure that results in sunburn varies from over 60 minutes for the low category to less than 10 minutes for the extreme category. It takes approximately 5 times longer to cause sunburn of the least susceptible skin type, brown to dark. The most susceptible skin type develops red sunburn, painful swelling, and skin peeling when exposed to excessive sunlight. By contrast, the least susceptible skin type rarely burns and shows very rapid tanning response. What happens to incoming solar radiation? When radiation strikes an object, 3 different things may occur simultaneously. First, some of the energy may be absorbed. What happens to incoming solar radiation? When radiation strikes an object, 3 different things may occur simultaneously. First, some of the energy may be absorbed. Recall that when radiant energy is absorbed, the molecules begin to vibrate faster, which causes an increase in temperature. The amount of energy absorbed by an object depends on the intensity of the radiation and the object's absorptivity. In the visible range, the degree of absorptivity is largely responsible for the brightness of an object. Surfaces that are good absorbers of all wavelengths of visible light appear black in color, whereas light-colored surfaces have a much lower absorptivity. That is why wearing light-colored clothing on a sunny summer day may help keep you cooler. Second, substances such as water and air, which are transparent to certain wavelengths of radiation, may simply transmit energy, allowing it to pass through without being absorbed. Third, some radiation may bounce off the object without being absorbed or transmitted. In summary, radiation may be absorbed, transmitted, or redirected, reflected or scattered. Figure 2.15 shows the fate of incoming solar radiation averaged for the entire globe. On average, about 50% of incoming solar energy is absorbed at Earth's surface. Another 30% is reflected and scattered back to space by the atmosphere, clouds, and reflective surfaces such as snow and water, and about 20% is absorbed by clouds and atmospheric gases. What determines whether solar radiation will be transmitted to the surface, scattered, reflected back to space, or absorbed by the gases and particles in the atmosphere? As you will see, it depends greatly upon the wavelength of the radiation, as well as the size and nature of the intervening material. Reflection and scattering. Reflection is the process whereby light bounces back from an object at the same angle and intensity, figure 2.16a. By contrast, scattering produces a larger number of weaker rays, traveling in different directions. Scattering disperses light both forward and backward, backscattering, Figure 216b. Whether solar radiation is reflected or scattered depends largely on the size of the intervening particles and the wavelength of the light. Reflection and Earth's albedo. About 30% of the solar energy that reaches our planet is reflected back to space, Figure 215. Included in this figure is the amount sent skyward by backscattering. This energy is lost to Earth and does not play a role in heating the atmosphere or Earth's surface. The fraction of radiation that is reflected by an object is called its albedo. The albedo for Earth as a whole, planetary albedo, is 30%. The amount of light reflected from Earth's land-sea surface represents only about 5% of the total planetary albedo, Figure 215. Not surprisingly, clouds are largely responsible for most of Earth's brightness as seen from space. The high reflectivity of clouds is experienced when looking down on a cloud during an airline flight. In comparison to Earth, the Moon, which has neither clouds nor an atmosphere, has an average albedo of only 7%. Although a full moon appears bright, the much brighter and larger Earth would, by comparison, provide far more light for an astronaut's Earth-lit moonwalk at night. Figure 217 gives the albedos for various surfaces. Fresh snow and thick clouds have high albedos, good reflectors. By contrast, dark soils and parking lots have low albedos and thus absorb much of the radiation they receive. In the case of a lake or the ocean, note that the angle at which the sun's rays strike the water surface greatly affects its albedo. Scattering and diffused light. Although incoming solar radiation travels in a straight line, small dust particles and gas molecules in the atmosphere scatter some of this energy in different directions. The result, called diffused light, explains how light reaches the area under the limbs of a tree and how a room is lit in the absence of direct sunlight. Further, on clear days scattering accounts for the brightness and the blue color of the daytime sky. In contrast, bodies like the Moon and Mercury, which are without atmospheres, have dark skies and pitch-black shadows, even during daylight hours. Overall, about 1/2 of solar radiation that is absorbed at Earth's surface arrives as diffused, scattered, light. Blue skies and red sunsets. Recall that sunlight appears white, but it is composed of all colors. Gas molecules more effectively scatter blue and violet light that have shorter wavelengths than they scatter red and orange. This accounts for the blue color of the sky and the orange and red colors seen at sunrise and sunset, Figure 218. On clear days, you can look in any direction away from the direct sun and see a blue sky, the wavelength of light more readily scattered by the atmosphere. Conversely, the sun appears to have an orange to reddish hue when viewed near the horizon, Figure 219. This is the result of the great distance solar radiation must travel through the atmosphere before it reaches your eyes, see Table 2.1. During its travel, most of the blue and violet wavelengths are scattered out. Consequently, the light that reaches your eyes consists mostly of reds and oranges. The reddish appearance of clouds during sunrise and sunset also results because the clouds are illuminated by light from which the blue color has been removed by scattering. The most spectacular sunsets occur when large quantities of fine dust or smoke particles penetrate the stratosphere. For 3 years after the great eruption of the Indonesian volcano Krakatau in 1883, brilliant sunsets occurred worldwide. In addition, the European summer that followed this colossal explosion was cooler than normal, which has been attributed to the loss of incoming solar radiation due to an increase in backscattering. Large particles associated with haze, fog, and smog scatter light more equally in all wavelengths. Because no color is predominant over any other, the sky appears white or gray on days when large particles are abundant. Scattering of sunlight by haze, water droplets, or dust particles makes it possible for us to observe bands, or rays, of sunlight called crepuscular rays. These bright fan-shaped bands are most commonly seen when the sun shines through a break in the clouds, as shown in Figure 220. Crepuscular rays can also be observed around twilight, when towering clouds cause alternating lighter and darker bands, light rays and shadows, to streak across the sky. In summary, the color of the sky gives an indication of the number of large or small particles present. Numerous small particles produce red sunsets, whereas large particles produce white, gray, skies. Thus, the bluer the sky, the less polluted, or drier, the air. Absorption of solar radiation. Although Earth's surface is a relatively good absorber, effectively absorbing most wavelengths of solar radiation, the atmosphere is not. As a result, only 20% of the solar radiation that reaches Earth is absorbed by gases in the atmosphere, see Figure 215. Much of the remaining incoming solar radiation transmits through the atmosphere and is absorbed by the Earth's land-sea surface. The atmosphere is a less effective absorber because gases are selective absorbers, and emitters, of radiation. Freshly fallen snow is another example of a selective absorber. Snow is a poor absorber of visible light, reflecting up to 85%, and, as a result, the temperature directly above a snow-covered surface is colder than it would otherwise be because much of the incoming radiation is reflected away. By contrast, snow is a very good absorber, absorbing up to 95% of the infrared heat radiation that is emitted from Earth's surface. As the ground radiates heat upward, the lowest layer of snow absorbs this energy and, in turn, radiates most of the energy downward. Thus, the depth at which a winter's frost can penetrate into the ground is much less when the ground is snow-covered than in an equally cold region without snow, giving credence to the statement the ground is blanketed with snow. Farmers who plant winter wheat desire a deep snow cover because it insulates their crops from bitter winter temperatures. The role of gases in the atmosphere. Heating Earth's surface and atmosphere. The greenhouse effect. Figure 221 shows that the majority of solar radiation is emitted in wavelengths shorter than 2.5 micrometers, shortwave radiation. By contrast, most radiation from Earth's surface is emitted at wavelengths between 2.5 and 30 micrometers, placing it in the long end of the infrared band of the electromagnetic spectrum. Heating of the atmosphere requires an understanding of how gases interact with the short wavelength incoming solar radiation and the long wavelength outgoing radiation emitted by Earth. Figure 221, top. Heating the atmosphere. When a gas molecule absorbs radiation, this energy is transformed into internal molecular motion, which is detectable as a rise in temperature, sensible heat. The lower part of Figure 221 gives the absorptivity of the principal atmospheric gases. Note that nitrogen, the most abundant constituent in the atmosphere, 78%, is a relatively poor absorber of incoming solar radiation. The only significant absorbers of incoming solar radiation are water vapor, oxygen, and ozone, which account for most of the solar energy absorbed directly by the atmosphere. Oxygen and ozone are efficient absorbers of high-energy, short-wave radiation. Oxygen removes most of the shorter wavelength UV radiation high in the atmosphere, and ozone absorbs UV rays in the stratosphere between 10 and 50 kilometers, 6 and 30 miles. The absorption of UV energy in the stratosphere accounts for the high temperatures experienced there. More importantly, without the removal of most UV radiation, human life would not be possible because UV energy disrupts our genetic code. Looking at the bottom of figure 221, you can see that for the atmosphere as a whole, none of the gases are effective absorbers of radiation with wavelengths between 0.3 and 0.7 micrometer. This region of the spectrum corresponds to the visible light band, which constitutes about 43% of the energy radiated by the Sun. Because the atmosphere is a poor absorber of visible radiation, most of this energy is transmitted to Earth's surface. Thus, we say that the atmosphere is nearly transparent to incoming solar radiation and that direct solar energy is not an effective heater of Earth's atmosphere. Students sometimes ask, what causes leaves on deciduous trees to change color each fall? The leaves of all deciduous trees contain the pigment chlorophyll, which gives them a green color. The leaves of some trees also contain the pigment carotene, which is yellow, and still others produce a class of pigments that appear red in color. During summer, leaves are factories that generate sugar from carbon dioxide and water by the action of light on chlorophyll. As the dominant pigment, chlorophyll causes the leaves of most trees to appear green. The shortening days and cool nights of autumn trigger changes in deciduous trees. With a drop in chlorophyll production, the green color of the leaves fades, allowing other pigments to be seen. If the leaves contain carotene, as do birch and hickory, they will change to bright yellow. Other trees, such as red maple and sumac, display the brightest reds and purples in the autumn landscape. We can also see in figure 221 that the atmosphere is generally a relatively efficient absorber of long-wave, infrared, radiation emitted by Earth. See the bottom right of figure 221. Water vapor and carbon dioxide are the principal absorbing gases, with water vapor absorbing about 60% of the radiation emitted by Earth's surface. Therefore, water vapor, more than any other gas, accounts for the warm temperatures of the lower troposphere, where it is most highly concentrated. Although the atmosphere is an effective absorber of radiation emitted by Earth's surface, it is nevertheless quite transparent to the band of radiation between 8 and 12 micrometers. Notice in figure 221, lower right, that the gases in the atmosphere, N2, CO2, H2O, absorb minimal energy in these wavelengths. Because the atmosphere is transparent to radiation between 8 and 12 micrometers, much as window glass is transparent to visible light, this band is called the atmospheric window. Although other atmospheric windows exist, the one located between 8 and 12 micrometers is the most significant because it is located where Earth's radiation is most intense. By contrast, clouds that are composed of tiny liquid droplets, not water vapor, are excellent absorbers of the energy in the atmospheric window. Clouds absorb outgoing radiation and radiate much of this energy back to Earth's surface. Thus, clouds serve a purpose similar to window blinds because they effectively block the atmospheric window and lower the rate at which Earth's surface cools. This explains why nighttime temperatures remain higher on cloudy nights than on clear nights. Because the atmosphere is largely transparent to solar, short-wave, radiation but more absorptive of the long-wave radiation emitted by Earth, the atmosphere is heated from the ground up. This explains the general drop in temperature with increased altitude in the troposphere. The farther from the radiator, Earth's surface, the colder it gets. On average, the temperature drops 6.5 degrees Celsius for each kilometer, 3.5 degrees Fahrenheit per 1,000 feet, increase in altitude, a figure known as the normal lapse rate. The fact that the atmosphere does not acquire the bulk of its energy directly from the sun but is heated by Earth's surface is of utmost importance to the dynamics of the weather machine. The greenhouse effect. Research of airless planetary bodies such as the Moon have led scientists to determine that if Earth had no atmosphere, it would have an average surface temperature below freezing. However, Earth's atmosphere traps some of the outgoing radiation, which makes our planet habitable. The extremely important role the atmosphere plays in heating Earth's surface has been named the greenhouse effect. As discussed earlier, cloudless air is largely transparent to incoming shortwave solar radiation and, hence, transmits it to Earth's surface. By contrast, a significant fraction of the long-wave radiation emitted by Earth's land-sea surface is absorbed by water vapor, carbon dioxide, and other trace gases in the atmosphere. This energy heats the air and increases the rate at which it radiates energy, both out to space and back toward Earth's surface. Without this complicated game of pass the hot potato, Earth's average temperature would be -18 degrees Celsius, 0 degrees Fahrenheit, rather than the current temperature of 15 degrees Celsius, 59 degrees Fahrenheit, figure 222. These absorptive gases in our atmosphere make Earth habitable for humans and other life forms. This natural phenomenon was named the greenhouse effect because greenhouses are heated in a similar manner, figure 222. The glass in a greenhouse allows shortwave solar radiation to enter and be absorbed by the objects inside. These objects, in turn, radiate energy but at longer wavelengths, to which glass is nearly opaque. The heat, therefore, is trapped in the greenhouse. Although this analogy is widely used, it has been shown that air inside greenhouses attains higher temperatures than outside air in part due to the restricted exchange of warmer air inside and cooler air outside. Nevertheless, the term greenhouse effect is still used to describe atmospheric heating. Media reports frequently and erroneously identify the greenhouse effect as the villain in the global warming problem. However, the greenhouse effect and global warming are different concepts. Without the greenhouse effect, Earth would be uninhabitable. Scientists have mounting evidence that human activities, particularly the release of carbon dioxide into the atmosphere, are responsible for a rise in global temperatures, see Chapter 14. Thus, humans are compounding the effects of an otherwise natural process, the greenhouse effect. It is incorrect to equate the greenhouse phenomenon, which makes life possible, with global warming, which involves undesirable changes to our atmosphere caused by human activities. Earth's heat budget. Globally, Earth's average temperature remains relatively constant, despite seasonal cold spells and heat waves. This stability indicates that a balance exists between the amount of incoming solar radiation and the amount of radiation emitted back to space. Otherwise, Earth would be getting progressively colder or progressively warmer. The annual balance of incoming and outgoing radiation is called Earth's heat budget. Annual energy balance. Figure 223 illustrates Earth's annual energy budget. For simplicity, we will use 100 units to represent the solar radiation intercepted at the outer edge of the atmosphere. You have already seen that, of the total radiation that reaches Earth, roughly 30 units, 30%, are reflected and scattered back to space. The remaining 70 units are absorbed, 20 units within the atmosphere and 50 units by Earth's land-sea surface. How does Earth transfer this energy back to space? If all of the energy absorbed by our planet were radiated directly and immediately back to space, Earth's heat budget would be simple: 100 units of radiation received and 100 units returned to space. In fact, this does happen over time, minus small quantities of energy that become locked up in biomass that may eventually become fossil fuel. What complicates the heat budget is the behavior of certain greenhouse gases, particularly water vapor and carbon dioxide. As you learned, these greenhouse gases absorb a large share of outward-directed infrared radiation and radiate much of that energy back to Earth. This recycled energy significantly increases the radiation received by Earth's surface. In addition to the 50 units received directly from the Sun, Earth's surface receives long-wave radiation emitted downward by the atmosphere, 94 units. A balance is maintained because all the energy absorbed by Earth's surface is returned to the atmosphere and eventually radiated back to space. Earth's surface loses energy through a variety of processes: the emission of long-wave radiation, conduction and convection, and energy loss to Earth's surface through the process of evaporation, latent heat, figure 223. Most of the long-wave radiation emitted skyward is reabsorbed by the atmosphere. Conduction results in the transfer of energy between Earth's surface to the air directly above, while convection carries the warm air located near the surface upward as thermals, 7 units. Earth's surface also loses a substantial amount of energy, 23 units, through evaporation. This occurs because energy is required for liquid water molecules to leave the surface of a body of water and change to its gaseous form, water vapor. The energy lost by a water body is carried into the atmosphere by molecules of water vapor. Recall that the heat used to evaporate water does not produce a temperature change and is referred to as latent heat, hidden heat. If the water vapor condenses to form cloud droplets, the energy will be detectable as sensible heat, heat we can feel and measure with a thermometer. Thus, through the process of evaporation, water molecules carry latent heat into the atmosphere, where it is eventually released. In summary, a careful examination of figure 223 confirms that the quantity of incoming solar radiation is, over time, balanced by the quantity of long-wave radiation that is radiated back to space. Box 2-3. Solar power. Nearly 95% of the world's energy needs are derived from fossil fuels, primarily oil, coal, and natural gas. Current estimates indicate that, at the present rate of consumption, we have enough fossil fuels to last about 150 years. However, with the rapid increase in demand by developing countries, the rate of consumption continues to climb. Thus, reserves will be in short supply sooner rather than later. How can a growing demand for energy be met without radically altering the planet we inhabit? Although no clear answer has yet emerged, we must consider greater use of alternate energy sources, such as solar and wind power. The term solar energy generally refers to the direct use of the sun's rays to supply energy for the needs of people. The simplest, and perhaps most widely used, passive solar collectors are south-facing windows. As shortwave sunlight passes through the glass, its energy is absorbed by objects in the room that, in turn, radiate long-wave heat that warms the air in the room. More elaborate systems used for home heating involve active solar collectors. These roof-mounted devices are normally large blackened boxes that are covered with glass. The heat they collect can be transferred to where it is needed by circulating air or fluids through pipes. Solar collectors are also used successfully to heat water for domestic and commercial needs. In Israel, for example, about 80% of all homes are equipped with solar collectors that provide hot water. Research is currently underway to improve the technologies for concentrating sunlight. One method uses parabolic troughs as solar energy collectors. Each collector resembles a large tube that has been cut in half. Their highly polished surfaces reflect sunlight onto a collection pipe. A fluid, usually oil, runs through the pipe and is heated by the concentrated sunlight. The fluid can reach temperatures of over 400 degrees Fahrenheit and is typically used to make steam that drives a turbine to produce electricity. Another type of collector uses photovoltaic, solar, cells that convert the sun's energy directly into electricity. Photovoltaic cells are usually connected together to create solar panels in which sunlight knocks electrons into higher energy states, to produce electricity, Figure 2d. For many years, solar cells were used mainly to power calculators and novelty devices. Today, however, large photovoltaic power stations are connected to electric grids to supplement other power-generating facilities. The leading countries in photovoltaic capacity are Germany, Japan, Spain, and the United States. The high cost of solar cells makes generating solar electricity more expensive than electricity created by other sources. As the cost of fossil fuels continues to increase, advances in photovoltaic technology should narrow the price differential. A new technology being developed, called the Stirling dish, converts thermal energy to electricity by using a mirror array to focus the sun's rays on the receiver end of a Stirling engine, Figure 2e. The internal side of a receiver then heats hydrogen gas, causing it to expand. The pressure created by the expanding gas drives a piston, which turns a small electric generator. Latitudinal heat balance. Because incoming solar radiation is roughly equal to the amount of outgoing radiation, on average, worldwide temperatures remain constant. However, the balance of incoming and outgoing radiation that is applicable for the entire planet is not maintained at each latitude. Averaged over the entire year, a zone around Earth that lies within 38 degrees latitude of the equator receives more solar radiation than is lost to space, Figure 224. The opposite is true for higher latitudes, where more heat is lost through radiation emitted by Earth than is received from the Sun. We might conclude that the tropics are getting hotter and the poles are getting colder. But that is not the case. Instead, the global wind systems and, to a lesser extent, the oceans act as giant thermal engines, transferring surplus heat from the tropics poleward. In effect, the energy imbalance drives the winds and the ocean currents. It should be of interest to those who live in the middle latitudes, in the northern hemisphere, from the latitude of New Orleans at 30 degrees north to the latitude of Winnipeg, Manitoba, at 50 degrees north, that most heat transfer takes place across this region. Consequently, much of the stormy weather experienced in the middle latitudes can be attributed to this unending transfer of heat from the tropics toward the poles. These processes are discussed in more detail in later chapters. Heating Earth's surface and atmosphere in review. The seasons are caused by changes in the angle at which the sun's rays strike the surface and the changes in the length of daylight at each latitude. These seasonal changes are the result of the tilt of Earth's axis as it revolves around the sun. Energy is the ability to do work. The two major categories of energy are, 1. Kinetic energy, which can be thought of as energy of motion, and 2. Potential energy, energy that has the capability to do work. Temperature is a measure of the average kinetic energy of the atoms or molecules in a substance. Heat is the transfer of energy into or out of an object because of temperature differences between that object and its surroundings. Latent heat, hidden heat, is the energy involved when water changes from one state of matter to another. During evaporation, for example, energy is stored by the escaping water vapor molecules, and this energy is eventually released when water vapor condenses to form water droplets in clouds. Conduction is the transfer of heat through matter by electron and molecular collisions between molecules. Because air is a poor conductor, conduction is significant only between Earth's surface and the air immediately in contact with the surface. Convection is heat transfer that involves the actual movement or circulation of a substance. Convection is an important mechanism of heat transfer in the atmosphere, where warm air rises and cooler air descends. Radiation or electromagnetic radiation consists of a large array of energy that includes X-rays, visible light, heat waves, and radio waves that travel as waves of various sizes. Shorter wavelengths of radiation have greater energy. These are four basic laws of radiation. 1. All objects emit radiant energy. 2. Hotter objects radiate more total energy per unit area than colder objects. 3. The hotter the radiating body, the shorter is the wavelength of maximum radiation. And 4. Objects that are good absorbers of radiation are also good emitters. Approximately 50% of the solar radiation that strikes the atmosphere reaches Earth's surface. About 30% is reflected back to space. The fraction of radiation reflected by a surface is called its albedo. The remaining 20% of the energy is absorbed by clouds and the atmosphere's gases. Radiant energy absorbed at Earth's surface is eventually radiated skyward. Because Earth has a much lower surface temperature than the Sun, its radiation is in the form of long-wave infrared radiation. Because the atmospheric gases, primarily water vapor and carbon dioxide, are more efficient absorbers of terrestrial, long-wave, radiation, the atmosphere is heated from the ground up. The selective absorption of Earth radiation by atmospheric gases, mainly water vapor and carbon dioxide, that results in Earth's average temperature being warmer than it would be otherwise is referred to as the greenhouse effect. The greenhouse effect is a natural phenomenon that makes Earth habitable. Human activities that release greenhouse gases, primarily carbon dioxide, are the villains of global warming, not the greenhouse effect as it is often, but inaccurately, portrayed. Because of the annual balance that exists between incoming and outgoing radiation, called the heat budget, Earth's average temperature remains relatively constant. Averaged over the entire year, a zone around Earth between 38 degrees north and 38 degrees south receives more solar radiation than is lost to space. The opposite is true for higher latitudes, where more heat is lost through outgoing long-wave radiation than is received. It is this energy imbalance between the low and high latitudes that drives the weather system and in turn transfers surplus heat from the tropics poleward.